Hello, my name is DeGuzman, and today, on behalf of my wonderful co-authors, I will be presenting our work titled Reduction of Motion Complexity as an Objective Indicator of Cybersickness in Virtual Reality. In this work, we found a relationship between motion complexity and user discomfort. This was done by conducting an initial investigation of motion complexity as an objective indicator of cybersickness. Our investigation consisted of analyzing the motion tracking data from two previous cybersickness studies. According to a recent meta-analysis by Zalasko and Weisker, the number of participants in both experiments are among the largest sample sizes from contemporary VR locomotion experiments. In particular, pay attention to the total number of sessions and trials in each experiment. This will make more sense in a moment. Before we get too far into it, though, what exactly is motion complexity? In this work, we are using the definition proposed by Kilkenny et al., in which motion complexity is the number of dimensions or degrees of freedom needed to describe 95% of the variance in movement. From this definition, they derived the D95 complexity score, which is based on principal component analysis. And because we are using principal component analysis, we needed a sufficiently large sample size to achieve sufficient sampling adequacy. Hence, the large number of sessions and trials that we have in each of our motion datasets. So why motion complexity? How did we get here? Well, motion data has been shown to be a promising objective indicator of cybersickness, and we believe that motion complexity could be a new angle for analyzing motion data. And this idea was the result of seeing the work by Peck and Guth in which they measured embodiment using movement complexity. Both embodiment and cybersickness are extremely challenging to measure, and this is because of the variance caused by the individual differences of the user, as well as having to rely on self-reported subjective measures. Since motion complexity has been shown to predict self-reported embodiment scores, we started wondering if this same relationship existed between motion complexity and cybersickness. In our analysis, we apply the D95 complexity score measure to two datasets. So the first of our datasets takes into account 6 degrees of freedom head movement data. This is the position and rotation of the head-mounted display, representing the physical motion generated by the user. This is the same derivation used by Kilkenny et al. Because virtual locomotion is also associated with cybersickness, we propose a complexity score that uses 9 dimensions. So in our 9 DOF movement datasets, it takes into account not only the physical movement of the head-mounted display, but also the position and rotation of the XR camera rig in the scene. Now, to calculate our complexity estimation, we start by applying principal component analysis on the motion data for each trial. This outputs eigenvalues that represent the amount of variance explained by a given principal component. Next, we sort the eigenvalues in descending order, so that finally we can loop through the array of each data matrix's cumulative proportion of variance. This is so that we can determine the fewest number of dimensions needed to explain at least 95% of the variance in motion. Now that we've defined our complexity measures, let's take a look at the experiments that provided the motion data we'll be using in our analysis. For the sake of time, this will just be a high-level overview. Experiment 1 uses the motion data from Wu and Suma Rosenberg's work, where they look at the efficacy of field of view restrictors with adaptive size and shape based on the optical flow in the scene. This experiment uses a 2x3 mixed design with the environment type as its between variable and the mitigation type as its within variable. Experiment 2 uses motion data from Ni et al.'s evaluation of the novel cybersickness reduction technique called peripheral teleportation. They used a between subjects design based on the mitigation type. Both experiments used virtual locomotion controlled by the controller's thumbstick to move. They instructed participants to just stand in place and not walk. However, participants were able to physically rotate their heads. Each experiment collected the following measures. However, in this analysis, we were only interested in the discomfort scores collected at the end of each trial, as well as the motion tracking data from the session. We did not aggregate the per-trial discomfort scores and instead looked at the individual ratings per trial. This allowed for a finer-grained analysis of data across all trials, seeing how discomfort changed over the course of exposure. So to investigate a potential relationship between motion complexity and discomfort score, we created a linear mixed effects model. And into this model, we plugged in the following linear regression equation, which uses discomfort score as its output variable and our complexity scores and mitigation as the predictor variables. This is because we are interested in the influence of our 6-DOF D95 and 9-DOF D95 complexity scores, as well as the mitigation condition on participants' individual discomfort score ratings. The following are the hypotheses that we used to guide our analysis. Hypotheses 1A and B were included to validate our statistical model. These are meant to confirm the previously reported effects on cybersickness reduction using the individual discomfort scores. Hypotheses 2 and 3 are completely new hypotheses to evaluate our proposed D95 motion complexity measure. Moving on to our results. In both experiments, the mitigation technique has a significant effect on participants' discomfort scores. The optical flow restrictor and peripheral teleportation conditions both had lower discomfort scores than their respective control conditions. These results confirm the previously reported main effects using our linear effects mixed model, thus supporting the validity of analyzing discomfort scores on a per-trial basis. Moving on to our second hypothesis, the 6-DOF D95 complexity score had a significant effect, but this effect was only seen in experiment 1. For hypothesis 3, our 9-DOF D95 complexity score, it had a significant effect on discomfort score seen in both experiments. From these results, we can see that there exists a relationship between motion complexity and user discomfort. In our analysis, we actually saw that one additional dimension is needed to explain the variance. There was a decrease in discomfort score. It is important to note, though, that these findings do not contradict previously proposed theories on causes of motion sickness. Furthermore, our results indicate that our 9-DOF complexity score has a higher sensitivity than our 6-DOF complexity score. In regards to limitations and future work, this was just an initial investigation. So our findings only show the potential of motion complexity as an objective indicator. Future work will have to validate its use as a cybersickness measurement instrument. And seeing how our higher dimension 9-DOF complexity score was more sensitive, future work can also consider incorporating more tracking dimensions into the measure. Finally, both of the experiments we analyzed only had participants standing in place, so evaluations during physical locomotion tasks are necessary. To summarize, this work we introduced applying the D95 complexity score to cybersickness research. By doing so, we uncovered a relationship between motion complexity and user discomfort. We also provide support for motion complexity as an objective cybersickness indicator. Motion complexity shows much promise as it is a more dynamic indicator that requires no additional instrumentation. Thank you all so much for listening.